Today I'm going to be talking about open source AI and that most open source AI isn't, and what we can do about that. So imagine yourself in a situation where we're all familiar with the story. You want to develop some software. So you define some requirements, maybe you select a framework, you've got some representative data, maybe you even have some unit tests written. This is the thing that I want to build. You select a contractor and you pay that contractor to build your software. Software gets built, you get shipped a binary blob, an executable that you can't poke at. You can try to reverse engineer it or disassemble it, but maybe you're not allowed to do that. You try to fix bugs, you've got security vulnerabilities. This is closed source software development. We all know that. That is, by definition. Let me talk you through a rhyming story. So you got some definition requirements, you selected a framework, you've got some representative data, maybe quite a lot of the representative data, and you select a compute vendor and you use a lot of cloud compute, maybe you buy a GPU, train your model, and you get a bunch of weights. You get a binary blob. Now, it might have some vulnerabilities. It might, make some incorrect inferences. Sometimes you don't know what's really going on. It's hard to fix. You can throw more data at it. And the lesson here is that, is this really that different? So let's take a step back. What is free and open source software? Based on different accepted definitions. And fundamentally, it boils down to a few things. You can use it for free. You're freely allowed to do what you'd like with it. You can distribute it and redistribute it for free. You're allowed to do that. You have that freedom. But also, one of the most important bits is there's freedom of modification and of understanding. If somebody sent you a compressed, they took JavaScript, they shrunk it down, they minimized it, and gave you that, that's hard to work with. It's not the way that the user would work with the software and improve it. And so similarly, like shipping a bunch of weights for machine learning is not the way you would necessarily modify it. Yeah, that's an artifact you can use, but it's not the whole thing. You can't see what's going on. You can't understand it very well. So let's take a little bit of a step back. Okay, we're all talking about open source software versus machine learning. They're different. Okay, let's dive in a little deeper. I'll use a couple of my favorite definitions of AI and ML, and there's many, but machine learning, what is it? It's programming with data. Another way to think about it is compression with generalization. You're taking a bunch of data, you're shrinking it down, and you're generalizing it in a flexible way as opposed to just compressing it. Now, AI, my favorite definition is it's hard computer science problems just haven't been solved yet. Great, blanket definition. You'll hear this from some of the old guard at AAAI and similar conferences. But fundamentally, it's just machines doing smart things. So one way to look at this is to cut the field into are we going towards a goal where measuring goodness, or are we trying to measure accuracy and measure how much it mimics something? And another axis is the classic AI trade-off of exploration versus exploitation. Exploration is there's knowledge that I don't know, there's uncertainty that I'm attempting to resolve, and exploitation is I have knowledge and I'm trying to work with it and ratchet in there. There's many types of AI, machine learning, and ways to define this, but in general, we're sort of talking about this big picture. If we're going to develop software or some artifact that does something in the space, how do we make sure that it's open source? Let's drill down a little bit into machine learning. So you got some data. Let's take this really simple graph here, and you want to connect the dots. We can have a model with low variance, like this. There's two lines, one going up to the right, one going down to the right. Okay, it's pretty good, it's pretty robust, but it's maybe not as accurate. We can literally connect the dots, and we get very low bias, but we get high variance. And we always try to come up with what's a good model for all of this, something that sort of blends those in a robust, thoughtful way. Now, there's also discriminative versus generative models. And this is, from a stats perspective, am I picking the best answer, whether it's the mode, the mean, whatever it happens to be, or generative is draw from that distributions of answers. Okay, so from that, we're programming with data. These are the building blocks. If we're using decision trees, optimum decision trees, graded wizard random forest, anything in that domain, we've got some sort of input, the x-axis, and the y-axis is some sort of output, right? So if it's less than this, it's this answer. If it's greater than this, it's this other answer. There's many ways to blend these together and scaffold these together and build these into very powerful systems. Neural networks, the building block looks quite similar. This is one of the classic techniques. Basically clamp it at this level, have a linear function going upward, but there's many curvier variants as well. This technique is chosen for many reasons, including performance. But another technique is instance-based learning or case-based reasoning, where we have the same sort of building block, but instead of it being just a building block that we piece together like Legos, the anchor points are actual data points. This will become very, very important. Now, what does it mean to understand? If we're talking about open source and openness, understanding has to be a piece of it, and is it part of the fundamental definition? Knowable, comprehensible, we can measure, we can predict it. Are there causal mechanisms? What if something had been a little bit different? Can we communicate it? If we don't have that understandability, we're just building intellectual debt. One way to think about it is if we're replacing a scientific process with a black box, that isn't really helping science. It might help us achieve our short-term objectives, but we're building debt in terms of what we know, as opposed to if we discover the causal mechanisms, if we discovered what was going on, now we can advance it. And so one of the calls here is to use AI and ML to advance science, not replace the scientific method. Now, what does AI and machine learning really offer? Historically, there have been two main terms of art in the domain talking about what you can understand in there. Historically, interpretable meant you could see the inner workings of the algorithm. You could follow and reproduce the prediction or the decision or the output. Decision trees, I can follow that, right? Or linear regression, I can reproduce that. GAMs, but lately interpretability and interpretable has been eroded along with explainable. And what does it really mean? You have an interpretation, not necessarily the interpretation. And it's going along with the classic term explainable, where the roots of explainable mean you come up with the explanation, but an explanation might not be that great. So today, explainable basically is an ex post justification. Here's a reason why the model might have made the decision, but maybe not. Suppose that you're watching a sporting event and the coach makes an interesting decision in the game, and you're like, I wonder why. Ideally, you'd be able to ask the coach. Now, the coach might not tell you for various reasons, but let's say that your best bet is you can ask a commentator. And the commentator says, well, I know the sport, maybe I know something about the coach, I think it's this. That's what an explanation is. It might be right 90% of the time, but it might be entirely wrong. One of the players might have had a personal life circumstance, a major life incident that changed their mentality, and now that player needs to be removed. You won't necessarily know that. You won't know all the details. You'll just get an answer. Now, if we look at, let's say, neural networks, which are the de facto standard in many areas of AI today, especially generative AI, here is a simple data problem on TensorFlow Playground. Now, for those of you who've been around in this area long enough to remember TensorFlow Playground, it's a really cool tool that got a lot of people to use TensorFlow, a number of years ago. And the idea here is this particular data set, we've got a spiral of blue and a spiral of orange, and we want to build a model that predicts those, something very small to see how these things work and how to interact with such systems. Well, given all these neurons, again, this is a very, relatively straightforward, very, very tiny problem that this can run in your browser. Here's a model that, gets reasonable accuracy. It's not great, but can you understand what's going on in there? Would this be open source, even though you can see all the pieces, or is that just a binary blob? Even with such a small and toy problem, it's difficult to understand what's really going on in there. And you can see all the nooks and crannies on the right, the peninsulas, the islands, the places where the model could be exploited. Now, you can totally argue that this isn't a great model, and it's not. But when do you know whether the model is good or not, and whether you've done enough training? You can get convergence, but did it converge to the right thing? Now, many people working in machine learning are also very familiar with this, this classic paper and tons of publications related to this, where we can use those nooks and crannies and contours in the model and exploit it. So that we take something that the model might get good results on, like let's say that the panda here, 37% confidence. You add a little tiny bit of noise, and all of a sudden it gets it very wrong. These nooks and crannies are exploitable. Also, what data was used to train the system? The algorithm's optimized for the data. What is your loss function? What if if you give someone medication, that you want to give them as much as you can without going over a threshold, because then you have very adverse consequences. But if you don't give them enough, then you're not treating the problem. Things can have asymmetric loss functions or long tail of situation of all the data. If you would like to train a self-driving car to drive on a freeway with low traffic, sunny day, straight roads, you don't need a whole lot of training data to get good results. But Phil Koopman from CMU talks about there's even just in a 2x2 mile block around the Carnegie Mellon campus, you can find tons of bizarre situations that how do you train for that? We've got a statue of Fred Rogers, as a Tyrannosaurus Rex carrying two kids that appears near the campus because Fred Rogers was from there. Is that a person in a Halloween costume? What is that? It fooled a lot of the machines. Or if you've got a cobblestone road of ice and you've got a vehicle accelerating towards you with its brake lights on, what do you do there? Can you use transfer learning from something else? What is the data? What is that long tail? And what's your model really doing? Again, you don't know what it was trained on necessarily. Maybe you do, but what is the effect of the training? But what's really going on inside? We've got all sorts of biases, and even the Simpsons paradox shown here. I'm oftentimes surprised at the number of data scientists who are not aware of this really powerful result. But if you get data points as you see in this graph right here, it looks like they're going down and to the right if you're coming to the best fit line. But in reality, if you break apart the data into two different sections or two different groups, you can see that it now says going up to the right. Did your model really do the right thing? Did you break up the data in the right way? How do you know? And some empirical results have found that Simpson's paradox appears much more frequently in real-world data than you might otherwise believe. Have you tested in the training set when you're building this model? Did you say, well, this model didn't work so well? You've already done generations of model selection. Have you curated the data multiple times and iterated? If so, you might be overfitting because you're a human in the process. And similarly, going back to did you train on enough long tail of data? One of my favorite results was looking at the process of science and what we know and what we don't know. There was an article looking at parachute use to prevent death and major trauma from falling out of an airplane without does a parachute really help when you fall out of an airplane? And they found no evidence to support the claim that parachutes help you falling out of an airplane. That's because there were no randomized controlled trials. Does that mean they don't help? Of course not. But could the model generalize in that regard with no evidence? And where can it make those correct inferences and not? By the way, they did a controlled experiment with this a number of years after that, where people jump out of an airplane with and out of the parachute and found no evidence in change in mortality. Now, of course, the airplane was on the ground and they're jumping into a mat. But the idea here still remains, do you have the supporting data? Do you have the counterfactual data? So, okay, we don't know what these black boxes are really doing most of the time, but we're really easy to fool as people. One of the classic examples looking at fooling people because of just justifications, because you get an explanation out. Xerox machines were very popular many, many years ago in large companies. Before you'd have a meeting, before we had all this great technology, you had to print out the paper, make a copy of it, and make a copy for everybody in the meeting. Oftentimes there'd be long lines for these copy machines. So some folks asked, how can we get people to break social norms via an explanation? So they said, well, try to cut in line. That didn't work so well. You say, excuse me, I have 5 pages, may I use the Xerox machine? A lot of people let them in. If you said that because you're in a rush, more people, would let you into the line and cut ahead. But if you gave them just an absurd, explanation of, excuse me, may I use the Xerox machine because I have to make copies, they would let you ahead most of the time. Now, there's a lot of supporting evidence around this, but all we need is an explanation, and we believe that drops our guard. So if we've got these machines in these black boxes that we don't know what they're doing, and we get an explanation, we're more likely to believe them for better and worse. So here's an example of a very common technique and how it fails. SHAP is one of the de facto standards often used for what's known as feature importance in machine learning. What features drove a decision? So let's take a look at a really simple data set where we're going to take 4 random variables, A, B, C, D, and we're going to add those together, and that will be the target that we're trying to predict. If we build a gradient boosted random forest on this, and we to ask what features really drove this decision, in the black bars right there, you can see that A was a big driver, C was an even bigger driver, B had nothing to do with it, and D had very little. Well, if you look, A and B are quite strongly correlated. So the model optimized out and said, I don't need B, I only need A, so therefore, that's my explanation. When in reality, looking at a robust, what SHAP actually is intending, A and B are about equal, and C was even stronger, and D actually had a contribution as well, even though it was uncorrelated. So if we look at the status quo, let's say we add noise to a feature, as you can see here, with SHAP, it says, oh, this feature doesn't have a lot of noise, so therefore it's only column A. And as we add more and more noise, well, now it says they're all about equal. So depending on the amount of noise in a feature, it will say whether it's important or influential or not, which can be very misleading or hide problems in your data. If you're you're debating where to spend marketing dollars, if you're debating where to invest research money and effort, it can tell you the wrong thing and say that one thing is far more important than another. Now, if we come up with these robust feature contributions where we can actually drop the features instead of putting in the mean value like SHAP does, or coming up with an excellent feature importance for the model, instead of that, do it actually on the data itself, we can see that all three features are contributing equally well and get more illuminated on what's happening. This is important because, I just mentioned a few examples, but this is the Boston housing data set, which is a known problematic data set because one of the features was the percentage of people who are Black in the community and how that affected home prices. There's a lot of historical bias there, but as you can see, SHAP can say, oh, it didn't use that very much when actually it did. So it can be very misleading in extremely important social situations and socioeconomic situations. Now, what does understanding mean? We tend to use, especially my company and among some of my colleagues, we're using this term a little more frequently instead of explainable, interpretable, because it's a different term that hasn't been eroded. The idea here is that there's two main paths of understanding. If you're a subject matter expert in the data, you should be able to look at the result, the prediction, the estimation, the recommendation, say, here are the things that are like it, understand why not, and what's driving it, and be able to communicate that from the results that you receive to another human being. You shouldn't need to know about machine learning. On the other hand, if you're trying to understand and debug the model, debug the data, you should be able to reproduce every prediction with a finite number of steps, carry the units everywhere. Anybody who's had a civil engineering, a mechanical engineering, physics class, you might have had one of those professors who grades really harshly. You need your units every step and see every step of your work. Why do we hold ourselves any less accountable for machine learning when such techniques are available and are usable and performant? In civil engineering, if you don't communicate all those results, even if you get the right answer, people could die if you justified why you built a bridge the way that you did, and someone uses that piece to build another sub piece. Every step needs to be correct. And so what does this look like? For any prediction, we can see what data led to the decision using some instance-based learning and some of the more modern techniques in the space, and see not just that, but the counterfactuals, the probability density function around the decision, which is automatically calibrated. We don't need a separate calibrator for it. And see, oh, wait, this particular instance, this one piece of data is driving almost a huge percentage of the probability mass of this decision. We can look into it. Understand your data. What pieces of data are affecting the accuracy, precision, recall, RMSE, whatever your metrics you're looking at, positively or negatively. Those sort of techniques are available today, and the robustness that I mentioned before is also super important. If you instance-based learning techniques like KNN and some of the things we've produced at Hauso with a probability-based kernel, they're able to get robust against attack. There's not these nooks and crannies and holes that can be exploited. You can take, for example, ResNet, many of them, even gradient boosted random forests, from very high accuracy down to virtually zero by attacking them with modern techniques. There's about 20 odd common techniques out there, versus KNN and other instance-based learning are very robust, so that even if you do attack it, you don't lose much of the performance. Now, there's a number of myths that have been developed over history around interpretability and explainability. Some of them have had truth in the past. But none of them are true today. One of them is that X is all you need. Something is all you need, whether it's feature importance or a counterfactual. Well, that might be useful in one case, but it's not useful in others. It might be useful for explaining why something didn't happen and building trust around that, but it's not useful for debugging your data or learning what drove a particular decision particularly. An ex post explanation is good enough. This can be problematic with adversarial models, can lead to some of the same problems that I mentioned before, and not calibrating your model. Oh, I got 99% confidence, so I'm good. Well, was that calibrated? Is that actually accurate? Will it be correct 99 times out of 100 if you actually did an experiment in the wild? And another myth is that decision trees are accessible. Those of us who've been around tech for a long time, or programming law, okay, maybe decision trees are accessible to us, but a number of studies have found that they're not accessible to most people. And even those of us who understand them very well, if you get more than a dozen nodes, even more than like 5 nodes in your decision tree, it starts to get pretty heady. And another bit is that there's a idea that interpretability and accuracy, that there's a big trade-off there, and that used to be the case, but not so much anymore. Some of these techniques we're able to get on par with gradient boosted random forests today. So another question about open source, going back to what's in this model. So looking at the diffusion models, which are widely used for creating images, these models oftentimes have 15,000 to 1 or 50,000 to 1 compression ratios, billions of images compressed down to something that runs on a GPU. Can't memorize, right? It's kind of, there can't be too much in there. It turns out that yes, it is a small fraction of 1%, but there is some of the training data that is exactly or almost exactly to a low quality JPEG degree stored within that model and memorized. And so if you look at some of the LLMs that are being compressed down pretty far, like Llama 2 and the like, they probably have much less memorization, but there's probably some in there. And some of the larger ones, like for example, GPT-3, ChatGPT, those sorts of things have compression ratios of around 7 to 1. So there's a lot of memorizations going in there. And so where did the data come from? Was it rightfully used? Are you really sure? If you transfer this model from one jurisdiction to another, are you doing the right thing? Now, given all of that backdrop about what's in the model, what's it doing, how do these open source licenses apply? So there's the source code licenses, which are typically permissive or copyleft for open source. Documentation has similar licenses, and data, there's some new licenses that are coming out because those are it's sort of a new era of sharing data like that. But suppose we get a black box model. How do these licenses apply? Well, great question. What if it's trained on non-free material? And the trainers didn't use differentially private techniques to make sure that there's not memorization going on. What if it was trained on AGPL v3 code and without differential privacy, and now it emits code with the comments? There's a number of lawsuits that are pending and a lot of disagreements around this. And suppose that you ship, imagine you built a game engine, a game, you heard a drum beat and some music, you really like that drum beat from the song. You sample it down, you use that one drum beat as a sound. Great, okay, we can argue that's fair use, and most people will see that's fine. But imagine you accidentally shipped the whole song in the game and someone can get it back out. Is that copyright infringement? Is that the right thing to do? If you don't know what's going on inside your machine learning, you might be doing just that. So instance-based learning, your data is the model. We're just going to find the data that's most similar and interpolate. And this is what I've been talking about, where we can give similar types of performance, model performance. So if let's say you put source code in there, the instance-based learning can find the similarities between the source code, mash it up, and generate new source code that is similar to it. So all of those licenses can propagate, and you can see what's in the model and debug it. So in general, how do we fix this, given all these techniques? So the state of the art of these forms of machine learning is there. The probability space kernels that we have at Hauso. There's some other companies that are trying to do similar things with causal techniques and really be able to understand what's in there, see and debug it just the same way that you do source code. So use a model, use a technique that is understandable and debuggable. And further, try to use one that can give you the attribution through the data. So if you use instance-based learning, you can see these are the 12 data points that had the influence on it. So you can debug and trace it back. Or causal, so that you can actually debug and say, these two things that had some relationship with this other thing, it goes this way, or you learn that that's not true, you can fix it, you can update it. And if you don't need attribution, use differentially private techniques to make sure that the attributions are broken in a good way, in a responsible way, and use differentially private techniques responsibly. Know where you get the data from. Was there consent involved? Did you scrape it off of did someone upstream scrape it off of some piracy website? And there's issues with it. What are the rights of the people who created it? Did they consent? What are the impacts of the use of this data? And as I mentioned before, use these differential private techniques and synthetic data as appropriate when you can't publish it. Publish the performance characteristics. How believable is your model in different areas? And publish negative results like we do in science. And we need to do more of in science because if you built it in the lab, does it really work outside? Or you built it, everyone else can learn from this thing that didn't work. If we're putting code in models as we are, do we need some sort of a GCC runtime library exception for the output? Right, so maybe you want a GPL licensed piece of software, or maybe you want an MIT license, but if you use a GPL, is there an exception to make sure things generated could be used in the free and open ways that you'd like? And let's not compromise these open source fundamentals for short-term practicality. If we say, well, these black boxes are good enough, and we're going to stamp them as open source, I think we're also doing a disservice to open source software that has all these understandable properties and eroding our principles. So I'm sort of giving a call to arms here for let's keep this purity and transparency and keep science and machine learning as opposed to replacing it. One other piece of this whole puzzle is knowing where your data came from. The Nonprofit Data and Trust Alliance is focused on adoption for some large organizations, trying to get some standards around provenance and lineage to make sure that we do know that we're doing the right thing when data comes in. And this is a draft of the standard. I'd invite anyone who's interested in adopting provenance and lineage and tracing the data, tracing the rights, the consent, the quality, all that sort of stuff through your data to look at this standard, look at some others and adopt such standards. And you might have noticed that I've been talking about open source, and I really haven't talked about ethics. And fundamentally, if we can't see and debug and fix models and improve them and understand what's going on, ethics is really hard to do right. We can hand wave and say, oh, we kind of got good empirical results, but will they actually give good results? And so having a foundation of openness in our AI machine learning is essential for doing AI ethics the right way. So if you'd like to check out some of the open source that we're developing for a replacement for black box techniques in machine learning, I'd invite you to check out our GitHub account and all the open source we're doing there.